ChronoBlade is a free-to-play game produced by nWay. nWay came across some of our videos, and after some discussion we agreed that I would forge a sword for them that fits both with the ChronoBlade style but was also Viking influenced. Here you can see the sketch I sent to them. The whole sword is going to be 30 inches long with a 24-inch blade. Since the sketch does not completely convey the sense of such a sword, let's take a look at what I am really aiming for. Unlike previous swords, I'm working on a limited budget with a limited amount of time. Instead of a pattern welded sword, this sword is going to be made from 1075, a high carbon steel that is ideal for tough but sharp blades and still similar to steels used historically. I am using a 1.5 inch wide and 24 inch long piece. The first forging step is to isolate about 3 inches of material for the tang. By using a blacksmith helper, I can fuller the steel equally from both sides. The next step is to draw out the steel to at least 6 inches of length. As you might remember from the design sketch, the tang will be peened over the pommel. This requires slightly more material than other designs in which the tang is peened over the guard instead. Using the power hammer saves a lot of time for a one-person venture. Strong helpers with big sledgehammers would achieve very similar results. As you can see, I am putting a taper into the tang. This will allow the upper guard and pommel to wedge onto the tang, creating a strong mechanical connection. After the tang has been forged, it is time to create the point of the sword. To accomplish that, I hit the steel at a 45 degrees angle from both sides. The initial objective is to create a strong transition that later can be smoothly tapered. Since the hammering also causes some upsetting, which increases the thickness of the blade, I need to correct for that occasionally too. The next step in the forging process is to taper the sword from the widest point at the hilt smoothly into its tip. This also significantly increases the length of the sword. As we only started with 24 inches of material, but need at least 30 inches at the end, this is a required step to reach the final dimensions. In addition to using the power hammer, I also make corrections with the regular hammer until I'm happy with the overall shape. For this sword, the blade needs to be about 2 inches wide at its widest point. It then tapers down to 1 inch width a few inches before the tip. As I started out with only 1.5 inches wide material, the remaining width needs to be gained from forging. Forging in the bevels is the process that not only establishes the cutting edge but also helps in widening the sword. The initial pass is done with a jig on the power hammer, but all the fine tuning happens by hand. The ultimate goal is to create a shape that is completely straight and centered without any warps. In practice, this is quite challenging. Although difficult to see in the video, another trick I use is to wet the anvil with water. As the hammer hits the blade, the water between the blade and anvil gets vaporized, which blows off the scale forming on the steel. While examining the sword after I put in the bevels, I realized that the blade is not quite wide enough. To correct for this, I'm also forging in the fuller. Originally, I had just planned to grind it into the blade. Unfortunately, forging in the fuller after the bevels results in some twisting of the blade, which again I have to correct by hand. Finally, the blade has been completely forged and is reasonably straight as confirmed by visual inspection. The next step is to anneal the blade at 1500 Fahrenheit for an hour to relieve all the stresses that built up during the forging process. At this point, all the forging on the sword is complete. Most of the remaining work is grinding, refining the geometry and polishing. However, while the forging on the blade is finished, a lot of hot work for the guards and pommel still remain. Another really important aspect for a sword is its weight. You will see me tracking the weight of the blade and complete sword for the rest of the videos. Here it is still quite heavy. While forging gets me close to the final shape I want, to get more precise I measure the middle of the sword and make sure that the blade is completely symmetrical. Now the most time-consuming part starts. That would be the grinding of the fuller and the cutting edge. This requires a lot of precision and patience. I use blue layout fluid to describe where I want the fuller to end. Here I mark half an inch on each side of the blade for the cutting edge. This will result in a fuller that narrows towards the tip. The initial grinding happens with fairly coarse grit belts and the geometry is established iteratively. First I grind in the fuller and then I refine the edges. Afterwards I might go back and refine the fuller further. This takes a lot of time and great care needs to be taken that the edge remains straight and that the fuller does not become too deep. The weight check shows that I have removed about 350 grams. 1000 grams is still way too heavy though. As I mentioned before, it is an iterative process and so back to the grinder it is. At this point I'm also taking the opportunity to refine the transition from the blade to the tang. The amount of sparks is a clear indication that I'm grinding high carbon steel. Now it's time for another pass over the fuller. This is shown in 40 times the normal speed, and grinding by hand means that I need to frequently check that I keep clean fuller lines. The final step before heat treating is to draw file the sword, which has multiple advantages. It allows me to fine-tune the geometry by hand, and it also removes all vertical grinder marks. These could potentially be stress risers during quenching. This is also a time-consuming step, and so you are seeing it here at 20 times the normal speed. Finally, it's time to harden the sword by heating it up to critical temperature and then quickly quenching it in high-speed quenching oil. I use a temperature-controlled kiln to bring the sword up to 1500 degrees Fahrenheit. At this temperature, the carbon is dissolved in the steel matrix. This is called austenite. By quenching it quickly, the carbon cannot move back into its normal configuration and the result is martensite, which is very hard. This is also the moment where the sword might break or twist horribly. It can be quite stressful. Here, everything looks fine. The sword is still pretty straight and there were no noises indicating any kind of fracture. The file just skids over the steel and does not bite, a sign that the sword was hardened successfully. A lot of work still needs to be done before the sword is finished, but this is a good place to stop for now. If you enjoyed this video, take a look at my other videos and subscribe to my channel. See you next time.